We are Team 22095, or Long-Term Surveillance via Solar Power UAV Group. We are sponsored by the National Aeronautics and Space Administration, or NASA for short. Our team members include Chase Chosek, Jackson Dahl, Omar Fuerte, Cooper McCoy, Jeffrey Northcutt, and James Roddle, and we are Team Sky High. Team Sky High was originally tasked with designing a fully autonomous, solar-powered UAV capable of 1 month flight time at a minimum altitude of 10,000 feet, while remaining within a 500-meter radius circle. Additionally, the UAV must carry a 40-megapixel camera containing a communications bandwidth greater than 256 kilobits per second and must be equipped with GPS tracking and telemetry capabilities. All these requirements are accompanied by a 50-kilogram mass constraint. The full-scale model, as designed, will have a wingspan of 12 meters and a chord length of half a meter. This wing area would allow for the integration of the required 375 Maxion Sun Power C60 solar cells necessary for this endurance flight at a cruise speed of 13 meters per second. Team Sky High has purchased 2 composite expanded polypropylene foam remote control gliders for all system integration and hardware testing. This RC prototype has a wingspan of 2.4 meters and a chord of 0.19 meters. For hardware testing, the prototype flew with a 1x14 solar array consisting of the same C60 solar cells intended for the full-scale model. With respect to the power subsystem, the two main critical components we tested were the solar cells and individual battery cells. When researching solar cells, it was important that they possessed the high flexibility to sustain the wing deflection in flight and not break or fracture, as to avoid jeopardizing the integrity of the solar array. At the same time, they needed to be able to collect a sufficient amount of power. This is what led us to choose the monocrystalline SunPower C60 solar cells, known for their high efficiency and high flexibility. We chose lithium-ion Panasonic 18650B battery cells due to their efficient recharge capabilities and high depth of discharge. Pictured here is a trade study performed for our power subsystem, showing the 2-day continuous flight power graph for our full-scale glider. This graph includes the use of 375 solar cells and accompanying 300 battery cells. Factoring in our predicted power of 1.1 kilowatts collected from the solar cells and power required for flight being 12 watts, this graph proves that theoretically continuous flight is attainable with a 20% margin of error. In order to make our glider as power efficient as possible, we set out to optimize the flight profile of our aircraft. Ultimately, we wanted to set a max altitude that our glider would climb to, shut off the motor, and glide at cruise speed until it reached the set minimum altitude. At this point, the motor would turn back on and climb to the service ceiling once again. By doing this, we aimed to achieve as efficient a flight as possible, only using power when we needed to climb. Using our autopilot software, ArduPilot, we were able to set the flight path and profile of the drone before takeoff and even make in-flight modifications. We also enabled a feature to allow the autopilot to automatically detect any geothermals that the UAV might cross while flying along its predetermined path. Essentially, this would give us free lift as the motor would not be required to climb. In order to maximize lift at our low airspeeds, determining what airfoil to use was a critical step in the research process. We targeted airfoils that would provide high lift at low Reynolds numbers since ultimately our UAV would not be traveling very fast. Initially, this led us to find the FX74CL5 140 airfoil. However, we quickly identified a potential hazard due to the high camber the airfoil possessed. As we planned to wrap the airfoil in a heat shrink film, we were worried that the high camber and sharp trailing edge of the airfoil would cause the filament to tear and compromise the structure of the wing. To mitigate this risk, we moved to the NACA 4412 airfoil. After analysis, we concluded that the NACA 4412 gave comparable values of lift for our cruise speed of approximately 13 meters per second. Using the program XFLR5, we were able to directly compare these two, along with other airfoils, to visualize the CL versus CD curves to analyze which airfoil would give us the most promising results. As far as the internal components of our UAV go, the control subsystem contains the majority of our aircraft's operational hardware required for automated and manual flight. The flight controller is the autopilot, or essentially what controls the UAV when the automated flight mode is engaged. Using the autopilot mission planning software, this is what allows us to set a mission profile beforehand and make in-flight adjustments as needed. The stick adapter is what houses the flight controller and keeps it level during flight. The GPS module connects via micro USB cable to the autopilot and is what provides our GPS tracking and telemetry capabilities, which is one of our original project requirements. The airspeed sensor provides readings from the pitot probe that is located on the right wing. This enables us to give a live reading of how fast the UAV is traveling at any time. Finally, the Tyrannus receiver is what connects to the radio, or remote control, allowing the UAV to be flown manually by a pilot on the ground. Thankfully, due to modern technology, we were able to find all these components and not have to compromise for size or excessive weight. By 3D printing some shelves, we were able to neatly organize the components within the fuselage of the UAV and still keep them level during flight. After completing hardware certification testing, component calibration, and system integration, Team SkyEye established 2 primary testing objectives for the 3 initial flight tests. The first objective was to prove that our designed system architecture was functional for flight. This includes all hardware and software associated with achieving manual as well as automated flight. This was accomplished first through a pre-flight test, followed by a maiden flight. The primary objectives of this maiden flight were to determine flight characteristics such as cruise velocity, while also verifying control surface inputs and authority. This was all accomplished before briefly enabling an automated flight mode and concluding the flight with a manual landing. Secondly, in order to prove our power gathering and storing scheme was successful, 2 flights of increasing flight time were performed. During these flights, a single, nominally discharged 18650 battery cell was configured by connecting the battery to the charge controller, which was then connected to the wires from the battery and solar array system. Upon landing, the battery was removed and charged to full capacity to verify that the battery capacity had indeed increased during flight. I was very satisfied with our initial test flights. All the internal components, communications, and controls worked successfully in the maiden flight. We were able to manually pilot the UAV, and all control surfaces responded accordingly. We were also able to use the autopilot to fly the predetermined course and flight profile. We even managed to have a little fun. Our second and third test flights were also a success. The batteries that were connected to the solar array came back with a higher charge than when the UAV first took off. However, the slight change was very small, and not to the extent that we predicted. A positive trend of power collection was proven, though, as the battery used on the third test flight, being the longest of the day, had shown the highest charge after the flight. In future testing, we look forward to trying to identify why we are not collecting as much power as we once originally calculated. We also look to continue to optimize the charge controller and add some additional components, like a power display showing the performance of the solar array in real time. Our team overcame many challenges throughout this year, the biggest being the loss of 2 of our team members over winter break. Losing 2 vital team members shook the team and our foundation of our unit. It took some time to get back on our feet, and all of us had to take some additional responsibilities on and step out of our comfort zone to learn about some subsystems that may be outside of our area of expertise. By rallying around one another and working towards a common goal, we were all proud of the product that we were able to create, and we look forward to continuing our education and the advancement of our UAV.